All right, this is a GeoGebra model. This is a GeoGebra demonstration of the solution to the SIR model differential equations that we wrote down last time. So GeoGebra is a lot like Desmos. It has some pluses and minuses, but one big advantage for it that comes into play here is that it will numerically solve differential equations for us. So over on the left, I've inputted the differential equations that we talked about in the last video. The rate of change of S, which is a function of time Si and R, is equal to negative A times S times I, which is that same differential equation that we talked about in the previous video. Similarly, the rate of change of the infection rate is ASI minus BI, and the rate of change of the recovered population is BI. And this system of equations is actually really tricky to solve using actual algebraic techniques, but we can ask a computer to plot a very, very good approximation of it. So that's what we have set up here. And we can see it's started to do this. It's gone from time t equals 0 to time t equals 0.5. And before I hit play on this, I want you to take a moment and think about what you think each of these three curves is going to do. So we can see that our susceptible numbers are already decreasing, right? The total number of people who haven't ever had the disease is decreasing because I is increasing, people are getting the disease, and R is also increasing. So take a minute and pause this video if you want, and think about what you think what each of these three curves are going to look like, bigger picture. Okay, so I'm going to go ahead and hit play. So if I hit play on this, we can see this starting to draw these curves out. We see the number of infected people increase, and then at some point peak and start to decrease. And then as that's decreasing, or as this is going on, the total number of people who have recovered is increasing. The number of people who are susceptible, who haven't yet had it, is decreasing. So what's happening here is, now we're going back in time. Stop that. Let's just leave that there. So what's happening here is eventually, in this model, eventually everybody gets the disease. At some point we're peaking, so at around time t equals 2, I have no idea what these units are there. Maybe they're weeks, something along those lines. At t equals 2, the total percentage of people who are infected is something over 70% or over 60%, right? This is an incredibly high peak. If this happened in real life, hospital resources would be overrun. This is very much the peak that we wanted to flatten. So I just wanted to point out what happens if we change some of the parameters. So A is the infection rate, or actually let's do recovery rate first. B is talking about how quickly people are recovering. We can see how that changes what these various curves are doing. So if we were to increase B, we notice that, well, this green curve is increasing faster. People recover faster. The people in the recovered group should be increasing more. But not only that, the infection curve is going down. People are leaving the hospital quicker, so the total number of people who are currently infected at any given moment decreases. Okay. Another thing that we could do is increase or decrease the infection rate. If people catch this illness quicker, then we can see that, hey, everything happens sooner. The peak shoots up earlier and also gets higher. People get sick before they have a chance to recover. If this is lower, then everything's a little bit more spread out. Lowering this is very much the flattening the curve that I'm sure you have seen in the news. If we can reduce the infection rates, we can reduce the total number of people who are sick at a given moment. Okay, one other thing I wanted to point out is that if we happen to be in a situation where the recovery rate is sufficiently big, so both of these numbers, maybe if they're both around 1, and if I zoom out a little bit, and if I also change the time, so back, oh geez, what am I doing? Okay, back with this example, we were in the situation where the total number of people who are susceptible eventually drops down to 0. This S curve eventually gets to 0, meaning that everybody has had at some point gets this illness. If the infection rate drops, not only is this I curve, the total number of people who are currently infected, not only does that drop, but we also get a situation where the number of people who are susceptible, as the number of people who never had the disease, doesn't actually go to 0. So there are some people who never get the disease. In other words, the disease burns itself out before it gets to everybody. So when we try to do things like social distancing, we're really trying to drive this infection rate down, which not only decreases the total number of people who are sick at a given moment, but also will make it allow this to be in a situation where there are people who never get the disease. In today's society, obviously the goal is to reduce as many people as possible who get this illness, and any little bit of decrease in the infection rate across the board is going to help in a bigger picture. All right.